Qbert is a really fun Atari game that I am truly terrible at. My goal with this project was to create an AI agent that could play better than me. I would consider this at least above 500 to 600 consistently and able to get above 1500 regularly.
Stand by, my Qbert is a little rusty.
Using the OpenAI Gym Toolkit, I was able to create some simple agents, the first of which was a tree search. One of the major problems I ran into was that with each time step in the environment was not a move of Qbert or him shifting from one square to the other, or any of the other agents for that matter, but rather a single frame. Qbert, however, still has to make a choice about what action to take at every time step. As such, it was very difficult for Qbert to find a good move, as a reward might be 100 frames away, and that is quite a depth. I dealt with this problem by having successive trees look until they found a notable action, either reward or death. The primary agent could then take the corresponding actions to achieve the reward and or avoid dying. In this particular implementation, there was one subtree for every possible action, of which there are 6 in total. Each tree would check at each time step for a notable action. If one was found, it would return the time that that action occurred. Prime Qbert would then take this path until his move had been completed and then search again. This was obviously very computationally expensive. In addition, successors were very difficult to find, as slight changes affected exactly when the notable action was recorded to have taken place. The subtree might say the reward took place at time 67, but in the true game, the reward would be at 71. The copied environments would always start at the beginning, so even taking the same actions at the same times wouldn't result in an identical game state. These errors propagated, leaving a wide margin for error that often resulted in Qbert losing a life. Numerous attempts to make Qbert better, usually revolving around having a better idea of when he was going to die and therefore how to avoid his doom, mostly resulted in longer and longer computational times with no significant improvement in score. The second agent I attempted was a probabilistic agent that made decisions based on previous notable actions. For example, the more times Qbert had made the same move, the more likely he was to make a new move. And the new move would be determined by previous moves. If he had jumped up the left repeatedly, he might not want to jump to the right, as there would be a much higher chance he is on the rightmost section of the pyramid, and in doing so would fall into the infinite abyss of nothingness. There is a lot of room to expand in this algorithm, perhaps taking into consideration all moves and not just ones in the same direction. I believe that Bayesian statistics could also prove quite effective by updating the probability of taking a certain action based on what had been previously profitable given the sequence of actions beforehand. In addition, I believe that there's a potential to incorporate the two algorithms. Red shirt games are the subtrees specifically designed to find when prime Qbert will die, but the process results in the death of the Qberts in those subtree games. By having the red shirt games find when death was most likely and adjusting the probability of Qbert's moves accordingly, I think there's a good chance I would see significant improvement.
Let's get to know him a little bit, ask him some questions, and then we'll kill him.
The results of my algorithms are as follows, with a purely random agent for comparison. The searching algorithm was very consistent, but not very effective, whereas the random algorithm was highly erratic, with a lower average, but the possibility of doing much better. In conclusion, I did not reach my goal. Instead, I made an agent that plays about as well as I do. And I think I understand now why Qbert uses the language he does.